Yeah, other paradigms are, for example, linear models. Yeah, in that case, a very simple idea: find a linear separation of classes. Yeah, like here. So you have the green class and you have the orange class, and you try to separate those two classes by a line in the two-dimensional case. In the higher dimensional case, it's a hyperplane. For example, one specific linear model is the support vector machine, which tries to find a maximum margin hyperplane. So a hyperplane which has a maximum margin between the nearest observations from both classes to the hyperplane. So these nearest observations are called the support vectors of the classes. So this one here is a support vector, and this one here is a support vector. Those are the guys that are on exactly on this margin. Yeah, we try to maximize this margin here. So the hyperplane tries to maximize the margin between the support vectors of the different classes here. Yeah, and we still need to do a little bit workaround here for the support vector machines, because very often, sometimes, no, not sometimes, very often, very often, sometimes doesn't work. So very often things are not linearly separable. Yeah, so the assumption for a linear separation is that, of course, the classes are separable by a hyperplane. If that's not the case, for example, in the famous XOR example, then we need to do some workarounds. So the first workaround for support vector machines is to introduce so-called soft margins. So within these margins here, we are allowed to make errors. So we allow also orange observations from the orange class in this area, yeah, which is an error, yeah, because they are on the opposite of the hyperplane of the decision boundary, but we allow them in this soft margin here, so to say. Yeah, and another workaround are kernels, yeah, especially for nonlinear problems, that we try to transform the data space into another representation in order. So, and the idea is that in that representation, in this new feature space, the problem is then linearly separable. Yeah, so and that's why kernels are actually kind of new representations. Yeah, so in that case, still we have to come up with a kind of handcrafted feature. But the trick here with SVNs and kernels is that we need not to actually materialize this transformation. So we can work on the original representations, but use the so-called kernel trick. So if you want to dig in there more, just have a look at the KDM slides or at the textbooks I gave you last week. Yeah, and finally, I want to just mention also the nearest neighbor classifier. This is a so-called instance-based learner, which means we use just distances or similarity measures to training objects. So we have our training objects here. The green ones are the dogs, the orange ones are the wolves. And now we have one that we don't know about it, so we just compute the nearest neighbor of the training objects to this query here, to this unknown guy. And this unknown object, the nearest neighbor is a dog, so we say, okay, this one is also a dog. Yeah? And of course, we can use not only nearest neighbor to determine the class label of a query, but also the k-nearest neighbors, and so on and so on. Yeah? So there are different variants in playing around with k and also with weighted k and stuff like that. Yeah? So here is the kind of big picture. Yeah, many more classification models are out there, neural networks and stuff like that. And once again, all these models basically differ in the shape of the decision boundary, because we don't know in a high-dimensional space what is actually the decision boundary. And base classifiers typically have a kind of non-linear shape, because they so we have different Gaussian distributions, and the area where the probability is equal to belong to both of the classes would be the decision boundary in that case. Yeah, linear classifiers have a linear separation of obviously. Decision trees have a kind of also linear, but well, it's not non-linear because we have a combination of several axis parallel linear separations, and k-nearest neighbor are also non-linear in the case that they somehow do something like Voronoi cells around the objects of the training data. Yeah? So you see those different methods have different decision boundaries, and depending, of course, on the data, some do better, some do worse. Yeah? So it's always a good idea to just throw all the bunch of methods you have on a problem and see what's coming out actually. Yeah? And for that purpose, of course, we need to know how to evaluate the accuracy of a model. And before we talk about that, we should talk about the problem of overfitting, because the question is how to do the evaluation, especially what to use for the evaluation. Well, we have our labeled data, so we know the outcome of our predictive model, at least for the objects that are already labeled. Yeah. So we could use, of course, the data that is already labeled that we use for training, also for evaluating how well the training actually worked. Yeah, but of course that is a kind of vicious thing, because if we train and evaluate a classifier on the same data set, here in that case the results may be misleading, because we aim, of course, at a good accuracy for all objects from the data domain, not only from the data set but from the data domain, but the quality for objects that we haven't seen so far in O is unknown in general, of course. Yeah? But we want to be also good for those objects. So if the classifier is only optimized for those objects that we already know, it will produce maybe very, very good results for O, for the objects in O that we know, but not necessarily for not yet seen objects. Yeah? And in the worst case, which is memorization, auswendig lernen in German, the worst case is we just memorize the decision for all objects from O, and then for all objects not seen so far, which are different to any objects of O, we have just a random decision, because we don't know how to decide, since we just memorized the observations that we had for training. And now if something comes in and we have to predict the class level for this one, and we haven't seen any of these we haven't seen this observation so far, and we just have to have memorized what we've seen so far, we can have only a random decision in that case. Yeah? So that would be the worst case of overfitting in that case. So the results from the application of a classifier to O, the labeled data, is not a realistic view for the performance of this classifier applied to any data set or data object, data observation, which could happen actually. Yeah? Especially those that are coming up, which we want to predict. So first of all, overfitting, underfitting. Once again, what is overfitting? Overfitting occurs when the classifier is too optimized to the training set. Yeah, could be many different reasons for overfitting. For this optimization to the training data, it could be because the training data is noisy. Yeah, we have bad quality of the training data, noisy, missing or wrong values, uncharacteristic training sets, of course, also, or also simple things like unbalanced class frequencies and stuff like that. Yeah, or a bad model which is so specific that is basically memorizing. Yeah, so decision trees by design tend to be very specific, tend to overfit in that case. Also, neural networks are extremely complex. So the more complex a model is, the higher the probability, or the higher the danger that this model actually overfits. Yeah? So always keep this in mind. So we have a kind of overfitting tendency of the models by design, but in addition we have other reasons possible for overfitting, like bad quality of training data, unbalanced class frequencies and stuff like that. Yeah? And it's overfitting versus underfitting. So there is also underfitting. Underfitting happens only very rarely, but it can occur, especially then the classifier is too simple. For example, look at this one here. For example, if we try to use a linear model for this one here, which is obviously, so the decision boundary between red and black here is a circle. So there is not a linear decision boundary. And if we try to apply a linear model here, that will be somewhere here or here or here or wherever. Obviously, this model is too simple in order to to model this very, very complicated situation. But that happens very, very rarely. Yeah. So mostly the problem is overfitting. So underfitting you will see in just very, very poor prediction or evaluation quality. Yeah? Okay.